All right, so last week over Zoom, we finished our work on linear programming, although we'll be coming back to it. And I started talking to you about the probabilistic method. Which is just a fancy name for the idea that if you're trying to find something with certain characteristics, you should just generate something random and hope that it has the characteristics that you're looking for. This is used often in combinatorics to prove the existence of certain combinatorial artifacts. And we're going to be focusing on using it algorithmically to prove the existence of a solution to an algorithmic problem with certain characteristics. And we've already talked about two examples of this. We talked about max cut. Okay. And from the perspective of a combinatorialist, our probabilistic method proved a theorem that there always exists a cut of value at least m over 2, right? Because we gave this simple randomized procedure, put the vertices randomly on one side or the other, and we said the expected value of this cut is m over 2. And the only way that the expected value of the cut can be m over 2 is if at least some values of the cut are at least m over 2, right? This is not Lake Wobegon where all of the cuts are above average. Algorithmically, and this is an existential statement, and one of the interesting things about these randomized about the probabilistic method is that you can use it to prove the existence of things that you can't check, right? So there are certain properties which are NP-complete to check, or computationally very difficult to check. But you can show that a random artifact probably has that property, right? And by doing that, you show that there exists an artifact with that property, even though you can't construct it efficiently or possibly at all. But we can also look at this as an algorithmic statement, right? Which is that we can always find a cut of value at least m over 2, which is also a 2 approximation to the max cut, right? If our cut value is at least m over 2, then whatever the value of the maximum cut is, it is at most m. So we are within a factor of 2 of the maximum cut value. And so we have a 2 approximation algorithm. Yes? Then the other problem that we looked at was set balancing. Where we have a collection of sets, of subsets of a ground set, and we want to divide the ground set so that each of the sets is evenly balanced between the two sides. So we have sets S1 through Sn, and I'm going to use the same letter for both of these just to keep it simpler, because it's a pretty abstract problem anyway. And we want to we want to partition, sorry, let me say 1 through n. We want to partition these integers such that each set is balanced, which is to say that the absolute value of the number of SIs on the left minus the number of SIs on the right is small for all SIs simultaneously. Okay, so we talked about this problem, and we again suggested that a random partition will give us something good, right? We noted that the random variable measuring the number of elements of the set Si on the left is a binomial distribution for however many elements are in Si with 50-50 probability of being on the left or right, right? And so we argued that its standard deviation was square root of n, square root of k, which was certainly less than square root of n. And we went on further to say that by a Chernoff bound, with high probability, the bias, this is called the bias, with high probability, the bias of this set is going to be less than square root of n log n. And since this is a high probability result, we can therefore say all the set biases are order root n log n simultaneously. So this is a proof that if you randomly partition the elements, the bias of any particular set will be at most square root of n log n. It is also a proof that there is always, that for any collection of subsets, there exists such a partition with that small a bias, right? And this is not generally stated in terms of approximation algorithms, right? For a given collection of subsets, there's some optimal bias that you can achieve, but this problem is usually studied just as a worst case, for any collection of sets, what is the best bias that you can achieve? And I think I also mentioned that this result was improved by Spencer using more precise, more sophisticated randomized random generation of solutions where he repaired them after they were generated to reduce this bias to 6 root n instead of root n log n. And there's been more progress since. Okay. Then we started talking about de-randomization. Okay. So in the case of these two problems, we have a randomized algorithm, which is to generate a random solution and then check whether it satisfies the conditions that we say are going to hold. But the question is, now that we know that this quality of solution exists, can we find it deterministically? And for that, I introduced you to the method of conditional expectations. Which essentially use the idea of self-reducibility, which we've already discussed. And said that we can set one vertex indicator x sub v at a time using the fact that the expected value of the cut is equal to 1/2 times the expected value of the cut given that you put vertex v on the left plus 1/2 of the expectation condition that you put the cut on the right. And if this has a certain value, then one of these conditional expectations has to have at least that large a value because this is the average of these two. So you can compute, or if you can compute these expectations, which we talked about how to do last time, then you can figure out which of them is larger, and you can set your variable xv to keep that to keep your expectation from decreasing. And you do this one vertex at a time, and eventually you've conditioned on all of the vertices, and now C is a random variable with a sample space of size 1, so it's a deterministic value, and you have found your cut. Yes? And this is where we finished last time. Okay? So now I want to apply the same ideas to the set balancing problem. Okay. And we immediately run into some problems. One of them is that we don't have any expectation to work with. Right? So we're going to have to do something fancier. Okay. So what do we have? We have a probability of things going wrong, right? We have some target, order root n log n, of bias, and we argued, we claimed this bound by saying, well, each individual set has a low probability of being biased, and now we can take a union over all of the sets. And that gives us an overall low probability of being biased. So the question is, can we apply this same idea of self-reducibility to this analysis, which is talking about probabilities instead of expectations? And yes, this is now known as the method of conditional probabilities for obvious reasons. What we're going to want to do is express our probability as something that we can condition on a particular placement of one of our items on the left or the right side, and compute that conditional probability and say the overall probability is an average of these two conditional probabilities, and therefore if the overall probability is small, then one of these two conditional probabilities must also be small. Yes? So is the general goal clear? Right? So for one set, this is relatively easy. Okay. We can talk about, let's let B sub I be the event that set I is too biased. Okay. Then we can say that, probability of B sub I, which we upper bounded by some, 1 over n squared or something, our high probability result, right? That this quantity is equal to 1/2 times the probability of BI given that xj equals 0 plus 1/2 times the probability of BI given that xj equals 1. Yes? And we can argue, just like in the case of the conditional expectations, that this probability is small. It is the average of these two probabilities. Therefore, one of these probabilities is small. So we can set xj to keep the probability of set I being biased small. Yes? But now this begins to go awry, because we actually have multiple sets, right? And it may be that set I wants to set xj to 0 in order to keep its probability small, but set k wants to set xj to 1 in order to keep its probability small. Right? So we have to get a little bit smarter. The general goal, right? We could talk about a general goal, right? We could say, let Q be the event that some set is biased. And we could do the same thing with Q, right? So on and so forth. Where do we run into trouble here? Yes.
Well, calculate the probability that of Q given x equals 0 would be
Exactly, right? We are now asking for a rather complex probability, the probability that that at least one of the sets has too large a bias. It's a union of many simpler events, and it's not clear how to compute that overall quantity, right? So let me say not easily computable. There might be a way, but I'm not sure what it is. So we're going to introduce another useful idea. Which is the idea of a pessimistic estimator. P hat. For an event for an event of interest, which and the idea is that we want this to be easily. So what characteristics do we want? We want it to be easily computable. That's why we're introducing it. We also want it to be an upper bound on the true probability of the event that we are looking at. And P hat is going to be condition. Its idea is to be something that you can condition, right? The same way as we condition the P's. But I will note that P hat might not be a probability. It just needs to act like one. So what we want is P hat of the bad event should be less than 1, so that we can say that the bad event might not happen. Okay. We also want that the minimum, let me say, the minimum of P hat of Q conditioned on x1 sorry, I'm getting a little lost in my notation. Yeah, let me do it this way. For a tree of settings of individual vertex settings. So remember, we're starting with no vertex set, and now we have we're making a choice about whether to set element 1 to be on the left or the right side, right? Then, after we've made that choice, we're going to make a choice about where to set element 2 on the left or right side. So this creates a binary tree of choices, right? So I'm looking at a particular piece of that tree, of a node and its 2 children. And in this position in the tree, I want the badness probability at A to be greater than the smaller of the badness probability at B and the badness probability at C. So again, this is a feature of the actual probability. Yes? Yeah, that's right. Greater than or equal. So this, again, is a feature of the real probability distribution that we need. So we are going to request that feature of this pessimistic estimator so that we can use it like a probability distribution. Okay. So basically, we just grabbed the things that we used about the actual probability distribution and said any other function that satisfies those conditions would also work for our method of conditional probabilities. So what we're going to do is we're going to look for such a function that is also easily computable. And then we will use it to run our method of conditional probabilities. Does that make sense? And so you see how this is enough to let us construct our solution, right? The pessimistic estimator says that at the root, right, at the root of the event tree, the probability of a bad event is less than 1. This step says that one of our children has a badness probability that is no larger. So that means that it will also be less than 1, right? And so we can keep going down to a child whose badness probability is less than or equal to 1 until we get to a leaf whose badness probability is less than or equal to 1. Yes? But if the leaf has a pessimistic estimator less than or equal to 1, then because the pessimistic estimator is an upper bound on the actual probability, sorry, this has to be at every node of the tree. Since the pessimistic estimator is an upper bound on the badness probability, the fact that it's less than 1, well, the actual badness probability at a leaf can only be 0 or 1, and so it has to be 0. So does anybody need me to write that out, or is that clear? Good? Okay, so the only question is, can we find such a pessimistic estimator? Yes. Exactly. Right? Our union bound is a pessimistic estimator. Right? So the probability that set I is too biased, conditioned on certain set values. I claim that is computable. Okay. If you think about it, what you essentially need to do is compute the value of the binomial distribution, right? The values that are set are going to put some of Si on the right and some of Si on the left, and there's going to be some that is not yet determined, right? And so there's a certain number that could go on the left that would create too much of a bias, and there's a certain number that could go on the right that would create too much of a bias, right? And so those are your sort of threshold values, and you now have an unbiased binomial distribution on the unset values, and you can simply compute using binomial coefficients the probability that you end up with too many of those indeterminate items going to the left or too many of them going to the right. Yes? Ask if that's not clear. All right, so given that this is computable, right, we can now talk about and we've arranged for this to be less than or equal to 1 over n squared, right, for our high probability result. It's actually enough for it to be less than 1 over 2n, actually, for this application, right? So that means that the sum of all of these is also computable and less than or equal to a half, right? So now we're in great shape. This is actually just the expected number of SI that get too biased, right? It's another way to talk about the union bound. Okay. This is something we can compute, but it is also an expectation. So we know that the rule of conditional expectations immediately applies, which means that it satisfies this axiom of a pessimistic estimator. Right? So we have now we have now found our pessimistic estimator. It's something that's easily computable because it's just sum of binomial distributions. It is the union bound, so it is an upper bound on the true probability. Its value is less than or equal to a half because of the way we chose our parameters, right? And it satisfies this smaller child property. So we can walk down the decision tree, and at the end, we will have a set that is appropriately balanced. Okay? Any questions about that? Okay. So now it's time for the next interesting idea of the lecture. So far, we have been using the most obvious possible probability distribution for generating our candidate solution and hoping that it works. Now we are going to try to be cleverer about what probability distribution we use before we make this argument that things work out well because of our sampling from the probability distribution. Okay. Let's see. Let's start with a classic problem called set cover. This is another one of these NP-hard optimization problems. We have a collection of subsets S1 through Sn, which are contained in the subsets of small integers. And our goal is to cover this collection of integers, a set or a collection of these Si, whose union is all of the elements in the ground set. That's why that's the sense that we're trying to cover it, right? So we just say the union over I element of our solution of Si contains 1 through m. And what we want is this collection to be as small as possible. Okay. I'm using two different parameters here for the number of sets and the size of the ground set because they actually are both interesting. And you can talk about approximation in terms of m, and you can also talk about approximation in terms of n, so on and so forth. So it's worth keeping them apart. So there are a variety of algorithms for this problem. It's been very intensively studied. It's a very basic problem in algorithms. For example, there's the greedy algorithm, which I teach in the advanced algorithms class, but I'm not going to teach it here because it's deterministic. Okay, so we're going to concentrate on randomized algorithms for this problem. Okay. And the way we're going to look at these randomized algorithms is we're actually going to go back to, we're going to return to linear programming. Okay. I'm going to write a linear program for solving this problem. Okay. LP solution. Okay. Oh, the set cover is NP-hard, by the way. So what I'm going to do is, it's funny. I haven't actually written down any LPs in this class because we've taken this geometric approach where it was all just about hyperplanes and constraints, and I never needed to write down any variables. But hopefully you've been around this long enough that you'll recognize what an LP looks like with variables. I'm going to use a collection of indicator variables. This is equal to 1 if Si is in the set, is in our solution. Okay. And what we're going to require is that for every element of the ground set, we want the sum of indicators for sets that contain V to be at least 1. And also to avoid letting us count sets more than once, we are going to require that the yi's be less than or equal to 1. Okay? So here I have a linear program that purports to solve the set cover problem, right? This constraint requires that I take at least one set that includes each V, and I'm just trying to minimize the number of sets that I take, right? So, do I have a linear program that solves the set cover problem? That would be a problem because linear programming is polynomial time and set cover is NP hard, right? So, yes? Exactly. So linear programming allows for fractional solutions, right? Rational solutions. This is what is known as an integer linear program. Okay, so this is a linear program which requires its variables to be integers. All right, and if I add that requirement that the variables be integers, then I do in fact have a representation of the set cover problem, right? Okay, what does that tell me about integer linear programming? NP complete, right? LP is NP complete. That's a bummer. If it's NP complete, I can't solve it. But here's where we can come back to this notion of the probabilistic method. I can relax it. I'm going through this a little bit quickly because I cover it in depth in advanced algorithms, but I think it should be clear. I'm going to relax this integer linear program and allow fractional solutions. And the hope is that the structure of the linear program sort of means that leads the fractional solutions to be kind of close in some way to the integer solutions. And as a second step, after I solve the LP, I'm going to round the fractional solution to an integer solution. Okay. Now, we all know about the usual form of rounding, right? If it's bigger than a half, round up. If it's smaller than a half, round down. And that works for some problems, but it doesn't work for this problem. You can pretty easily construct examples where all of the y's are very close to 0 in the optimum solution. So if you rounded that way, everything would be 0 and you wouldn't have a solution at all. Yes?
Just decrease the threshold of straw. It comes in
Yes. I mean, that's a plausible algorithm. I don't know if anybody's actually analyzed it. Okay. I'm going to show you a different technique that can be proven to work well. And the technique relies on the fact that these y's are between 0 and 1. In this class, what is a thing that is between 0 and 1? Yes. A probability, right? So we can think about yi as the probability that set I is in the solution. Okay? And that is a technique known as randomized rounding. Okay. What we're going to do is we will set our yi hat equal to 1 with probability yi. Okay. So this already gives us some nice consequences. In particular, sum of yi's is the expected number of sets taken. Right? Actually, that lets me, I should point to something else important. We relaxed the integer linear program, right? We allowed more solutions. That is not going to make the optimum worse, right? So the sum of yi's in our React solution is less than or equal to the optimum of the integer linear program. Yes? So, under this randomized rounding procedure, the expected number of sets that we take is less than or equal to the optimum. Yes? So that's nice. But it doesn't do everything for us because this tells us that our solution is optimal, but it doesn't tell us if our solution is feasible, right? The job of the sets that we're choosing is to cover all of the items. And the question is whether they do that. So what can we say about the probability that item J is covered? How would we compute that under this randomized rounding scheme? Yes? So, sorry, you answered last time, so yeah, go ahead. Exactly. So as is common, right, it's easier to talk about the complementary probability, the probability that an item is not covered, right, and then take 1 minus it. So what is the probability that the item is not covered? Well, it is the probability that you don't take any of the sets that contain it, right? So that is the product over J, over SIs that contain this element J of 1 minus yi. Yes? Yeah, go ahead.
This is at least 1 minus.
Exactly. So what we're going to do is we're going to look at this term, right? And 1 minus yi is less than or equal to e to the minus yi, right? So this is greater than or equal to 1 minus the product of e to the minus yi, which is equal to 1 minus e to the minus sum over these sets that contain j of the yi. And what do we know about that? What do we know about that sum? Yeah? It's at least 1 because of our linear program, right? So this is the point. The nice thing about linear programming relaxations is that they keep a lot of the structure of the problem that you want to solve, right? So here this turns this into 1 minus 1 over e. Okay? So every element has a constant chance of being covered by this random process. Yes? Okay, now that's not quite what we want because we want to cover all of the elements, right? But if we have a technique that, or an algorithm that works with a constant probability, how do we make it work reliably? Yeah? Amplification, right? If we repeat this some order of log n times, right? We have a constant chance of success in each attempt. So that means that we succeed in covering J with high probability, right? And now we take a union bound, and we can say that we cover all the items with high probability. Yes? And what is the total number of sets that we took? Well, we used opt sets in expectation each time, which means that we're going to use order log n times opt sets in expectation overall. So here we have a log n approximation to the set cover problem. Yes?
But just because like we get one set of sets that covers like each one individually, is that like how can we guarantee what if we find that?
That's the joy of with high probability statements, was that we can just apply union bounds, right? So through this repeated process, we can say that we got a set for J with high probability, and that means that the probability we failed to cover J is negligible. And now we just add those negligibles over all n elements that we're trying to cover, and it's still negligible. So the probability that we missed anything is negligible. Yes? Well, that is a very good question. And the answer is we don't know, because this is actually tied up in the P equals NP question. There are results on approximation hardness that show that you cannot get a better approximation than a certain amount for various problems. This was one of the huge breakthroughs of the 1990s that showed, it's something called the PCP theorem, which has nothing to do with PCPs, it's about probabilistically checkable proofs. And there's been like 20 years of beautiful work that show that if you can approximate such and such problem to within such and such factor, then P equals NP. And I believe, although I'm not a complexity theorist, so I don't keep these things top of mind, I believe that this is the threshold for, like, you can't do better than this unless P equals NP. But I would have to check the literature to be sure. Okay? The greedy algorithm also achieves a logarithmic ratio, but I think it achieves a log m as opposed to a log n. Right? So as I said, there are these two different parameters to think about. No, that's not right. It's also log n. So they're equivalent in terms of worst case bounds, but because the linear program sort of tracks the structure of the actual problem, I think it tends to work better in practice than the greedy algorithm. Okay. All right. Let me show you one more LP relaxation. This is a problem in VLSI wiring. So in VLSI, the world is basically Manhattan. You have a collection of channels on the chip that go horizontally and vertically. And you have a collection of sort of circuitry elements that have been placed on the chip. And now you need to run wires that connect different parts of the circuitry. And the wires have to run through the channels. Okay, that's the only place where they can be put. And the question is, but the channels have limited capacity. And the question is, how should you route your wires in order to fit them into the channels without violating the capacity limits? Okay. And I'm going to look at a special case of this, which is called one-bend wiring. I don't think this was made up by theoreticians. I think that there's actually I think it's actually bad to have too many bends in your wires. But we're going to look at the sort of most restricted case where you're only allowed to take one bend in the wiring between your two components, which really means that between a given starting point and a given ending point, you only have two choices for how to wire that connection. Yes? You have to decide whether you start horizontal or you start vertical, and then everything else is determined. Okay. So, I can make an integer linear program for this problem. Right? What I can do is I can have an indicator variable. I'm going to have xi0 equal to 1 if wire I starts horizontal, and xi1 equal 1 if wire I starts vertical. And again, if I think of these as indicator variables, 0 and 1, then they are an exact description of a candidate solution to the wiring problem, right? And now I can sort of measure the, yes, go ahead. Yes, I'm assuming that the component, of course, has lots of complexity inside of it, but the wire has to land at a certain spot in the component. Okay. So now I'm going to define Ti0 to be the set of i's such that wire I. So this grid is, of course, a graph, right? And I can think of each of these pieces of channel as an edge of this graph. So I'm going to write not Ti0, Te0 to be the set of wires that go through E when xi0 equals 1. And I'm going to write Te1 to be the set of wires that goes through edge E when xi1 is equal to 1. Yes? And now the problem of minimizing the congestion on a particular edge is pretty easy to write as a integer linear program. I say I want to minimize the limit, the congestion, such that each wire makes one choice about where it is going. And for every edge E, the sum over wires that hit it when they go horizontal of the indicator variable for that wire going horizontal, plus the sum of the wires that hit the edge when they go vertical of the indicator that wire went vertical should be less than this congestion bound. Okay, so unpacking this, after I tell you which wires go vertical and which wires go horizontal, this left-hand side tells me how many wires are going through a particular edge. Yes? And what I'm demanding is that W upper bound this number of wires going through edge E for every edge E. So W is essentially the maximum congestion encountered by any edge, and I'm trying to minimize that maximum congestion. Is that clear? Okay. So again, as an integer linear program, this exactly characterizes the feasible solution or the possible solutions to the wiring problem, but I can't solve it. But I can relax it and find a fractional solution. Of no worse W. Right? So how do I round it? How do I get back to an integer solution from this fractional solution? Well, again, given the setting, the thing to do is to look for something that can be treated as a probability. Right? And here I have these indicate, right? I probably should just have called this a single indicator, xi equals 0 or xi equal 1, right? But the point is that this requirement that these two values sum to 1 means that I can think about the probability of using the vertical wire or the probability of using the horizontal wire. Yes? Okay. So, round. Set xi hat 0 equal 1 with probability xi 0. And of course, xi 1 hat is the complement of this. Right? So that's a plausible rounding. And what does it do to the, what do I read off of the constraints here? What is this left-hand side telling me if I do the rounding this way? Right, so xi 0, I'm treating it as a probability I use the vertical wire or the horizontal wire. And this summation is over wires that use edge E if they start horizontal. Right, so what is this summation? Yes? Exactly, right? The LP constraint measures the expected number of wires through edge E when I do the rounding. Right? So this is pretty appealing, right? My rounding procedure minimizes the congestion in expectation. Right? Minimizes the expected congestion on any possible edge. Okay, that's pretty good, but expectations aren't enough for us because we have lots of edges, right? If we have a root n, let's say a root n by root n grid of n edges, right? Some of those edges are going to have a large deviation from their expectation. What can we do about that, or what can we say about that? Well, here we have a sum of indicator variables, and we have nice tail bounds for sums of indicator variables, right? So now we invoke tail bounds. Right? We basically apply the Chernoff bound on the congestion of any edge. Right? And as a very simple application of this Chernoff bound, I can say that with high probability, the congestion on E is at most W times log n, or order W log n. This is the usual Chernoff bound, right? We have a 1 over n chance of having a log n factor deviation from the mean. We've seen that over and over again with our Chernoff bounds, so I won't write it out unless somebody asks me to. Okay. But because this is with high probability, we can apply it simultaneously to all edges, right? Because there's only a polynomial number of edges. So, in summary, this gives us an order log n approximation to the minimum possible congestion. Clear? Okay. I would love for people to ask questions. It's great if you're confused and need something explained, much better than if you go away confused. So do ask if it's not clear. In fact, if W is large, then we're in a different realm of the Chernoff bound. We get a constant factor approximation. Right? If your expectation is already log n, then the Chernoff bound tells you that you're within 1 plus or minus epsilon of that with high probability. Right? So this is not fantastic if the channel capacity is very, very small. But if the channel capacity is quite large, then this becomes a very good approximation algorithm. Okay. Now, I covered the single bend version of this because it was easy to write down and didn't require a lot of background. But for those of you who are familiar with multi-commodity flow, okay, which is a generalization of max flow to having multiple sources and multiple sinks, right? You can write down a multi-commodity flow problem that basically says each of these components, right, that one end of the wire is a source and one end of the wire is a sink for a particular kind of flow, right? So think of this, right? This wire is carrying oil, this wire is carrying water, this wire is carrying boba tea, and so forth, right? And I have a different max flow problem I have a different flow problem for each wire that needs to be placed, okay? And you can write down a max flow or a multi-commodity flow as a linear program and solve it, and that gives you a solution in terms of flows. The problem is that the flows might be fractional, right? Your solution might send half of the flow this way and half of the flow that way, for example. Okay, but especially if you've seen this stuff, you know that a flow can be decomposed into fractional paths, which essentially turns it into, just like the problem we have here, a collection of fractional paths that go from the source to the sink, and their total capacity will be 1. So you can think of choosing one of those paths at random, and that is the generalization of this rounding scheme and has exactly the same analysis because it's still just a sum of indicator variables to measure the congestion. Okay. I will also mention that this method can be de-randomized using the pessimistic estimator approach. Okay. So you can use this to construct a solution deterministically as well. All right. So that was the basics of randomized rounding. Are there any questions? Okay, then let's take a break, and then I will get fancier. Everybody's too tired to get up?
I'm so tired.
I am. I was at dance camp all weekend. I can barely stand. But
Yeah.
I don't think you were.
To be honest, I think in expectation I'm also pretty tired. Also, I sent you an email on during the week.
Oh, yes. I think I have a meeting. I'll have to check. I may have a little bit of time after, but I'll have to double check my. All right, let's resume. Not that we have a lot of time left, but first of all, let me show you that de-randomization for wiring, or really for any LP which is done the same way as sort of a sum of indicator variables that you want to have close to its expectation, right? So we use a pessimistic estimator. And just like in the set balancing, it is just the expected number of, well, actually, let me go from the other direction. So here, if we think about one edge, has a sum of indicator variables associated with it, right? With a good expectation. And we want to say, we want to sort of walk down this decision tree for setting these indicator variables in a way which keeps every constraint close to its expectation, or keeps it from going high above its expectation, right? What we know is that the probability of a large deviation is small by the Chernoff bound. Okay. Now, unlike the set balancing, right, we don't have an exact formula for the probability of a large deviation, right? We're instead using an upper bound for the probability of a large deviation, right? But where did that upper bound come from? Recall that the way we bounded, when we had some random variable x as a sum of indicator variables, we said that the probability that x was bigger than 1 plus epsilon times its mean was less than the expectation of e to the tx over e to the t times 1 plus epsilon times mu, right? That was our derivation of the Chernoff bound. Yes? But what's nice about, and so let's just call this, well, the point is that this is computable, right? Okay. It's not a probability, it's an expectation, but it's a computable expectation, right? Because the x, remember, this is simplified as a probability over I of the expectation of e to the t times xi, because the xi are independent, right? And it's pretty easy. You can work out the value for the expectation of e to the txi when xi is a very, has a, you can go back and see, we worked out those probabilities in the derivation. So this is a computable probability, so you can compute the Chernoff bound associated with a particular x, and we know that that is less than 1 over 2n, say, by an appropriate setting of parameters. We're saying with high probability this doesn't happen, right? And now, just as with the set bias, sum these, right? The sum of all of these is less than or equal to a half. So the sum of the Chernoff bounds is computable. It is less than 1 at the root. And because it's an expectation, it satisfies the branching children property that we need, right? One of the conditional expectations, setting the value one way or the other, will be smaller than the one that you started with. Yes? That's this value that, if you go back to the Chernoff bound, I think it's 1 plus delta log 1 plus delta. You optimize it using calculus, and it's just it's a value that minimizes, right? This is a U-shaped function of t, and so you find the t that minimizes it, and that's the one that you use to get the best Chernoff bound. It's true for any t. Okay, you can find it in the notes. Yeah, I don't remember it off the top of my head. So, is what we're doing here clear? So again, we're not computing probabilities exactly, but we have a proxy for the probabilities that works the same way and lets us descend the tree by setting one wire at a time. Okay. All right, so that's it for randomized rounding of linear programming. Of linear programming solutions to approximation problems. Now I'm going to show you one of the seminal results of this area, which was discovered right here at MIT by Michel Gomans, who's in the math department, and his graduate student, David Williamson, who's now a professor at Cornell. And this is a more sophisticated relaxation technique. And they applied it to a problem, to the max cut problem. We had a 2 approximation through the most naive of all possible probabilistic generations, right? We just uniformly generated a partition and got a 2 approximation, okay? They went in a different direction. There wasn't an obvious approach that would yield value with linear programs. They didn't sort of come up with a nice linear programming relaxation of the problem. But there is a very nice quadratic programming relaxation of the problem. Okay? So I am going to, again, think about indicator variables, xi for vertex I, talking about whether vertex I is on the left or the right. Okay. The linear program is minimize the sum over edges ij in your graph, 1 minus xi times xj divided by 2, where xi, where all xi are, sorry, I need one more, actually I don't even need that, where xi squared is equal to what? So let's think about this a little bit. I will say, by the way, there's no integer restriction here. Okay? I don't have to add an integrality constraint. Okay? But notice that this quadratic constraint, that xi squared equals 1, means that there are only two possible values for xi, right? It's +1 or -1. And those represent the two sides of the cut. Okay? So let's think about what this constraint is measuring. Okay? What are the possible values for one of these terms for a given edge ij? Yeah? Exactly. If they're on the same side, then you have an xi squared here, right? They both have the same value. They square to 1. And you get 0. If they're on opposite sides, you have something in its negation. So you get a -1. Add 1, that's 2. Divide by 2, you get 1. So this is just counting the number of edges that have their endpoints on opposite sides. Yes? Yes, thank you. Sorry, I kind of have min cut really deeply drilled into my brain, so it's instinctive. Okay. Max cut is much harder, right? Max cut is NP hard. Min cut is trivial. It is. You can solve it in linear time, right? So everybody agrees that this is a quadratic programming formulation of max cut, and we didn't even have to add an integrality constraint. Great. What does that mean about quadratic programming? Yeah? It's NP hard. So what was the point? Well, the point is that this leads to a direction of a different kind of relaxation. Okay? Relaxing to fractions doesn't do anything, right? Even if we will allow fractions, this simple quadratic constraint forces integers. So we can't do a fractional relaxation. Instead, we are going to relax to vectors, which is bizarre, but turns out to be incredibly powerful. Okay? I'm going to write down this. Oops. Hij. 1 minus vi dot vj divided by 2, subject to xi dot xi equals 1. And that, of course, is just the norm of xi squared. What? Sorry, vi dot vi is equal to 1. Okay? So that's the relaxation. And what's amazing is that this relaxation is polynomial time solvable. Okay? This is what is known as a semi-definite program. Okay. Yes? It is not general. Sorry, in general, we don't specify it because we understand implicitly that if you're talking about n variables, then this relaxation or the polynomial time solvable version of this is going to be n-dimensional vectors. And you'll see why in just a minute. Okay. And sadly, if you constrain the dimension, like if you say, I want to solve this with two-dimensional vectors, then it gets NP hard again. Okay? But allowing you to have a large number of vectors works out fine. The reason is that a collection of vectors V defines a matrix V. Okay, capital V. Okay. And all of the dot products that we're constraining in this semi-definite program can be seen in the product VV transpose. Yes? I write down all of the rows in V. I am then multiplying all of the rows by all of the rows. Out comes a matrix of dot products, right? So I'm going to call this matrix D for the matrix of dot products. Dij is equal to Vi dot Vj. Yes? Okay. And what that means, the fact that D is a square of a matrix means that D is positive semi-definite. Okay. And you may or may not have encountered this in your linear algebra classes. Positive semi-definite is basically the matrix generalization of positive. It has a square root. What is the square root of D? It's V, right? V is a thing that if you square it, you get D. All right? But another definition of positive semi-definite is that all of its eigenvalues are non-negative. Okay? And so this semi-definite program can be stated. Also, the other thing I should say is, given D, you can find V. You can take the square root of a positive semi-definite matrix using something called the Cholesky decomposition. I should say, I'm running through this quickly because I'm not going to teach you any of the details of this. I am just giving you enough background so that I can say, whoa, we wave a magic wand and we get a solution to the semi-definite program. Okay? If you want to know how to actually solve a semi-definite program, that's a whole class in the OR department. Okay? So given D, you can find V using this Cholesky decomposition. And the semi-definite program is a collection, right? It was a quadratic program, but it's a linear program over D, right? So each of these constraints is a linear constraint on D. So a semi-definite program says, find me a positive semi-definite matrix that satisfies a bunch of linear constraints on its entries. Okay. Now what's amazing and deep is that the requirement that you be positive semi-definite can also be written down as a collection of linear constraints on the entries of the matrix. Okay. Unfortunately, it's an infinite number of linear constraints. Okay. So remember what I said that, so another definition of positive semi-definite is that for any vector y, y times d times y transpose has to be non-negative. Okay? Because y times d times y transpose is just yv times yv transpose. So it's a square. And so it's non-negative. Okay? So basically, each potential vector y gives a constraint on D that is a linear constraint. And